Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. Imagine walking through a forest 100 million years ago. The air is thick, humid, and carries a sharp, pungent aroma of pine and damp earth. While we cannot physically travel back to the Cretaceous period, nature has left behind a sophisticated chemical diary that allows us to breathe the same air as the dinosaurs, symbolically, at least. This diary is written in the language of terpenes, the complex organic molecules found within fossilized resin, or what we commonly call amber. For decades, we viewed amber primarily as a medium for preserving spectacular fossils like mosquitoes, feathers, or even tiny lizards. However, a new frontier in paleobotany and geochemistry is looking past the trapped insects and focusing instead on the amber itself. By analyzing the terpene archive, scientists are reconstructing the chemical composition of the prehistoric atmosphere with staggering precision. To understand this process, we first had to understand what terpenes are. Terpenes are a large and diverse class of organic compounds produced by a variety of plants, particularly conifers. They are the primary constituents of the essential oils that give trees their distinct scents. When a prehistoric tree was injured by an insect or a storm, it secreted liquid resin as a defense mechanism. This sticky substance was rich in terpenes, which acted as both a physical barrier and a chemical deterrent. As this resin flowed down the bark, it interacted with the surrounding environment, capturing air bubbles and moisture. Over millions of years, through a process called polymerization, the liquid resin hardened into amber. During this transformation, the terpene molecules didn't just sit there. They became a molecular record of the atmospheric conditions present at the moment of secretion. The breakthrough in this field comes from the study of carbon isotopes trapped within these terpene structures. Carbon exists in different forms, mainly carbon-12 and carbon-13. The ratio between these isotopes in a plant's resin is directly influenced by the concentration of carbon dioxide in the atmosphere and the level of humidity in the forest. When CO2 levels are high, plants tend to favor the lighter carbon-12 isotope. By extracting these molecules from ancient amber and running them through a mass spectrometer, researchers can calculate the exact CO2 concentrations of the deep past. This data is revealing a prehistoric world where carbon levels were often 5 to 10 times higher than they are today, fueling the massive growth of the giant flora that supported the largest land animals to ever live. But the terpene archive offers more than just CO2 data. It also provides a window into prehistoric oxygen levels. For years, scientists debated whether the atmosphere during the age of the dinosaurs was hyperoxygenated. By examining the oxidation states of specific diterpenoids and triterpenoids within the amber, geochemists have found evidence that suggests oxygen levels were remarkably stable for millions of years, though significantly higher than our current 21%. This high oxygen environment allowed for more efficient respiration in large organisms, but it also made the prehistoric forests incredibly flammable. The terpene archive often shows signs of charcoal and pyrogenic polycyclic aromatic hydrocarbons, suggesting that the lush, resin-heavy forests of the past were frequently subjected to massive, high-energy wildfires triggered by lightning in a high-oxygen atmosphere. Furthermore, the specific types of terpenes found in a sample can tell us exactly which species of trees dominated a particular region. This molecular fingerprinting allows us to map the migration of ancient forests as the continents drifted apart. For instance, finding specific resins usually associated with the southern hemisphere in northern European amber deposits tells a story of a much warmer, more interconnected world where tropical forests stretched almost from pole to pole. These molecules are essentially the biological black boxes of extinct ecosystems. When we analyze a piece of amber from the Baltic or the Dominican Republic, we aren't just looking at a pretty gemstone. We are reading a chemical spreadsheet that details the humidity, the temperature, the gas concentrations, and the floral biodiversity of a lost world. Understanding the terpene archive isn't just about satisfying our curiosity about the past, it's vital for our future. As we face rapid climate change today, looking at how the Earth's atmosphere responded to high CO2 levels in the past provides essential data for our climate models. The resin molecules prove that the Earth is a resilient, self-regulating system, but they also show how drastically the environment can change when the chemical balance is shifted. Each tiny amber bead is a piece of a puzzle, helping us piece together the history of the very air we breathe. By decoding these ancient scents and molecular structures, we are finally learning the true story of how our planet's atmosphere evolved to support life as we know it. For more incredible facts like this, don't forget to subscribe and turn on notifications.